the idea. Given a differential equation, given some sort of, remember differential equations, we have some sort of dy dx equals, right? And then fill in the blank. It could either be explicit, quick reminders, or implicit. Do you guys remember the difference?
You have to solve the dy dx with implicit.
Yeah, but explain why though.
Because the y is kind of trapped inside like a chain rule.
So the implicit is in terms of, basically it's f of, can I say this? F of x and y. There are x's and y's in the function.
Yeah.
Whereas for explicit, it's just in terms of x. Is that cool? Okay. Maybe I shouldn't use f because it's dy dx, but you guys know what I'm talking about. I'm just talking about the derivative as a function, right? So you're given some sort of derivative, okay? And with that derivative, there are many different things we can do with it. The AP can either ask us to use that derivative in order to form a slope field, so to find particular slopes and then to be able to visualize the flow. They can ask us to solve that differential equation, which is coming at some point soon. To solve that differential equation, which means basically anti-derive and figure out the original function, hopefully if possible. Or they could ask us to find particular solutions either with a slope field, or I should say in a slope field, or using integration. In a slope field or using integration. If they think about that field of slopes that you saw just a second ago, what could they give to us that would allow us to establish one particular one, even though it's showing the flows of all the different possible? Because remember, there's a plus c when you integrate, so there are infinitely many different solutions for every differential equation. But how could they establish it and say, no, I just want this one? They have to give us a point. They have to give us a point. And actually, technically, either way, wouldn't they have to give us a point? They have to give us some sort of clue. So either of these, you'd have to be given a point. But the difference is, in a slope field, you're going to be drawing, graphing the point, and then following the flow through the point, before and after. Or using integration, you're going to solve, you're going to have a plus c, you're going to have a constant in integration, and then you're going to plug in your point, solve for c, and have your particular solution to that one, right? The order of a differential equation is basically determined by the highest order derivative.
What does that mean, first derivative?
That means the differential equations can involve more than what you're used to. If you have this one right here, if you have a dy dx equals just some function in terms of x's or y's, it's technically called so dy dx. Or if it has y prime only, that's going to be a first order differential equation. I'll just say DBQ. It's actually a class in college. Some people call them DBQs. I like my abbreviation EQ and better, but that's okay. So then what would it take to have a second order differential equation? There has to be some sort of y double prime as well. I'm going to say y double prime. Meaning there could be a y, there could be a y prime, and there could be a y double prime, but y double prime is the highest order derivative. And the first one, like I said, could be a y or there could be a y prime. Of course there could be x's, that's always a thing, but this new terminology to kind of be aware of at least what they're talking about. So general solutions. You could have a slope field that shows the flow of all the different possible general solutions, or you could have an equation with a plus c that shows a family of antiderivatives. Particular solution, you have to be given some sort of point, some sort of clue that you plug in. Either you graph it on the slope field, or you use integration to solve for the plus c. That's all intro stuff. Why aren't you moving?
Good question.
There we go. So if this is a differential equation, now it's not exactly, we're precisely ready to go to the slope field right now. I'm not saying this is a slope field necessarily, but if we were to try to answer this question, determine whether the function or the functions below are solutions of the differential equation y double prime minus y equals 0. How would we be able to check? First of all, what kind of differential equation is this, technically? What order? Second order. Just new terminology. Because it has a y double prime inside. But if we were just checking, we're just able to experiment. So how can we solve this? Yeah. Just find y double prime and plug it in and say, hey, is it true? So y single prime of sine, cosine, y double prime of sine, derivative of cosine is negative sine. So what if I was to plug that in? What's negative sine minus? Remember, plug in the double prime minus. Does that equal 0? No. So is this a solution? Nope. What about the next one? Now, hold on. You're not solving for this. You're being given different possible solutions. You're saying, I don't know, do any of these ones work? That's all we're doing. And if you guys look at this differential equation, y double prime equals y, there are only certain solutions whose derivatives come back to equal the same as the original, right? So if you look at this, they have a trig, they have an exponential. Yeah, that makes sense, right? No powers are going to come back. No roots are going to come back. No logarithms are going to come back, right? But these ones are somewhat cyclic in nature. What's y prime? Y double prime. Hey, y double prime equal to y? Bingo. And one possible solution. This isn't the solution, this is a solution. True? Okay. So what if we were to go y equals c times e to the x?
It would just be e, c, d, x, e,
Same thing, right? If it's always the same, well, yeah, of course, that's going to be a solution as well. Now, this one has infinitely many solutions, but as you can tell, is he the same as him? No. But they're similar. Could we generalize letter B? What could we generalize him to be? Yeah. We could just throw in like another constant d, e to the negative x, if we really want to, and say, hey, these whole families of solutions are going to be, or these whole family of functions are going to be solutions to the differential equation. Anyway, that's just something silly if you see differential equations. If the AP gives you differential equations, especially with subtraction, be aware they might not always be asking you to actually solve for the solution. You have to look out, and only if they ask for solve for the solution, solve by differentiating, solve with separable differential equations, etc. They might not always be asking you to find it yourself. My page down button is not working. Let's go hit there. Let's do one more just to get used to the idea of being given funny directions. So now, for the differential equation xy prime minus 3y equals 0, verify that y equals c, x cubed is a solution. Then, find the particular solution. Oh, they better have given me something. Booyah, they did. Go. Verify. You can just show by demonstrating that it works. We're not proving. We're just verifying it works. Let's put this in here. Because when I've done, the problem itself has this experimenting. However, I have faith in this one. Maybe we could solve this without. And we'll see how that works in just a second. Just as an introduction to differential equations. But first of all, you guys verified by finding y prime, yeah? What did you get y prime to be?
3cx squared.
Then plug it in, chug it, you can say x times 3cx squared minus 3 times cx cubed doesn't in fact equal 0, and the answer was yes. So then how do you find this, the particular solution if you have the general form of the antiderivative? Plug it in, so I know that y is equal to 2, and x is equal to c times negative 3 quantity cubed, that would be negative 27, c is equal to 2 over 27, right? But that's not the solution. What are they talking? Ooh. Thank you. What does that mean? What are they referring to when they say the particular solution? They just want C, the constant of integration, that's enough. They want the actual equation. The solution to a differential equation says, hey, who is the original? So we put it all together, we would go back and plug in negative 2 over 27 for C x cubed. Now, this original function, he looks kind of easy. I mean, the differential equation was weird, but that doesn't look too hard. Maybe we could have gotten there a different way. All right, kiddos, especially my AB kiddos. What's another way of writing y prime?
dy dx.
So we could write x times dy dx minus 3y equals 0. Now, not all differential equations can be solved using our methods that you're about to see, but this one can. So question, how would you solve this differential equation? Especially my AB kids, try to hang in there, we're just kind of introducing it.
How do you solve it?
Good. Get rid of as much subtraction and addition as you can. And as I divide by x, what else do I want to do? So I'm moving the x's to the right, I'm moving the y's to the left. What is the purpose of that? Gerard, think through integrals. When you have an integral, you have it sandwiched with one differential, either just dx or just dy. We don't have it sandwiched together with both. So we're going to separate the two. And say, hey, you belong on the y side, you belong on the x side. So we're going to separate by moving dx to the other side. And now we have separation with separation of variables. We have the proper forms to go ahead and integrate. And why are we integrating? Because we have a derivative and we're trying to get to the original. We're trying to go back.
But can't we just do it the other way?
Well, if they give you an answer. Does that make sense? So I'm introducing how this actually could have been solved from the differential equation. Does that make sense? Okay, so on the left, what do we have? Who has a derivative of 1 over y? ln of y. Technically, couldn't we put a plus c? I suppose. So Gerardo, the integral on the left could have a constant of integration, all on its own. And then the derivative on the right, 3 ln of x, could have his own integral, constant of integration. But here's the idea. Ready? Two different constants of integration. Don't necessarily have to be the same. Couldn't I just subtract one constant from another constant and have a new constant? So the idea is I can have a c and a d and then an f, or I could just say, you know what, whatever. This constant is going to combine with that constant, so I can just go ahead and say, you know what, there's a constant of integration over here. Does that make sense? Now, if I was to get all the way to here, question, what would I have to keep doing? E to the. So I would do e, I need to undo the ln to get to that y. E to the. Then I end up with absolute value of y is equal to, what do I do here? I can move the 3 up as a power, good, so it's ln of x cubed, e to the ln will cancel. But wait a minute, what about this plus c? I have to think about properties of exponents.
Oh, it'll be times.
Exactly. And then think about this, ready? E to the c, Gerardo. Review for you guys from last year. Isn't that just a new constant? Because e raised to all sorts of different numbers, I could just represent that as another constant, right? So in theory, I can say, okay, well, the e to the c is arbitrary in the sense of, really, I could just see him as his own, and we could do subscripts like c1, c2, c3. There'd be a new c that I could just have being multiplied to represent the e to the c. E and ln cancel out, yeah? Struggle, there we go. So the absolute value of y is equal to e to the ln cancel. I have c, absolute value of x, quantity cubed. Technically, absolute value of y, remember sometimes he could be a positive change to a, well, hold on, wait a minute. If x is absolute value, then technically y is absolute value. Question, could y's sign be messed up by x?
Yeah. No, not in this case.
And if y is absolute value, then technically I could just say, well, I just need y to always be positive. How does that work? Well, hold on, I need y though. So the absolute value is trapping it. Technically, I could make this a little piecewise, do. It would take a little bit of work. I could make this a little piecewise in the sense of I could say y is sometimes positive for y, or y stays the same for y greater than or equal to 0. Y changes if y is less than 0. I could do some spiffiness like that. Then I would go ahead and plug this into greater than or less than, etc., etc. I could solve. But just for sake of simplicity, just because this isn't our main focus for today, I'm just trying to do a quick review. Guys, compare this form with the one over on the left. How are we doing?
This on the right is way.
Yeah, we're doing right? So let's go ahead and just take our initial condition. Let's plug and chug real fast, because we can plug and chug in the form that it's written. Then we can go ahead and say, okay, when y is equal to 2 and x is equal to negative 3, uh-oh, quick struggle. What's the dilemma if we go plug it in right now? We have a 2 and then a negative 3, that would be flipped to a positive. We'd have positive 2 over 27. So was our one on the left wrong?
Maybe it's plus or minus.
In some senses, when you have absolute value on either side, you guys remember when solving absolute value equations, you take away the absolute value, you put in a plus or minus? That's kind of the idea of what's going on. So we could go ahead and take away the absolute value of the y. We could put a plus or minus, but do you see how the plus or minus will basically get absorbed into the c? And so in a sense, without getting too complicated, we can kind of just take away both of those absolute values, and we can say, you know what, both of them would end up putting a plus or minus on the other side, and put both those pluses or minuses. If you get a new plus or minus, we can absorb that into our c, our constant, and say, you know what, he's going to end up to be what we need him to be. So then when we go ahead and plug a point in like negative 3, 2, we are able to get what we saw c to be on a page before, sorry, on the side before, negative 2 over 27. So y is equal to negative 2 over 27 is one solution. But maybe if you notice that c could be plus or minus, maybe we have a few more options and it's not just vertical translations of each other in the sense of the different possible solutions. So sometimes our solution might be positive, sometimes it might be negative. Depends on the clue that we're trying to connect it through. Okay, anyway, all of this was just a quick reminder for my A-Beers for last year. This one could be solved, but not every differential equation can. And that's where one of the purposes of the slope field comes in, because some differential equations are impossible to solve, at least not with those methods, with the integration by separation of variables. And for those that are difficult to solve, or even those that might be impossible to solve, slope fields are quite helpful to be able to still show us the movement, the behavior, etc. of original functions, even if we can't mathematically algebraically state them, which is kind of crazy to think about. So slope fields, as you guys were talking about in the beginning, fields of slopes. Think like a minefield, like Minesweeper sort of. In the sense of at all different places you have different things going on. But it's not necessarily the same. Slopes are determined by the slope at each point, so we'll just say the slope at, we'll just say, for instance, x1, y1 is going to be the same thing as the differential equation with x1, such that x1, y1 has gotten plugged in. Oops, there's a comment. In order to find the slopes, we need the differential equations. Okay, so that makes sense. Slope fields are based upon differential equations, but they are showing the definition down below. They're showing the family of antiderivatives as indicated by line segments with slopes determined by the differential equation, which I like to affectionately call the baby tangents. Lots of baby tangents. A whole field full of them. And then put them all together, and we provide a visual perspective of the original functions graph to answer when integrated. And once again, why is that useful? Differential equations are not always able to be integrated, at least not with our methods. So something that's too complicated for us to solve, we can still be able to know some things about it, which should kind of draw your attention back to last chapter when we were doing those crazy ones when we were trying to integrate something that we didn't know how to integrate, even with U sub that we hadn't done yet. We were doing that whole, all right, do we know a point? Okay, cool, we can make an integral, and even though we can't solve for the equation itself right now, we can at least find values. Put all those values together, we can see how it moves, how it shifts, how it shapes, how it behaves. That's what a slope field kind of does too.
Misty?
Yeah.
Maybe on days when people are absent, like when you know they're at home, you can like live stream the YouTube.
That's true. I think that might use up more of our bandwidth though, wouldn't it? Live streaming?
Maybe. It was just a thought.
It's a good thought. But our Wi-Fi is a bit spotty. So, let's say, sketch a slope field. Wait, I don't like it. Hold on. Sketch a, it shouldn't be a slope field. That is a slope field, right? What would be the right way of wording this question?
Sketch a graph.
Possible.
Yeah, possible, or I'll say particular. Is that okay? A particular solution for the differential equation y prime equals x minus y for the points -1, 1, 0, 1, and 1, 1. Now hold on. Does it make sense that this is a slope field for that differential equation? Really quickly. Now, what Sam was saying earlier was looking at the quadrants. Why? Well, because the quadrants, to some extent, we know how the x's and y's, not numerically how they are, but at least their signs. Like in the first quadrant, x is positive and y is positive, right? Second quadrant, x is negative, y is positive. Third quadrant, both are negative, right? X and y.
Should we draw because of the slope?
We're going to draw some in a second. Let's go ahead and just try to think through. Just because drawing that's going to... This might be something if you want it in your notes, it's better just to go online in the notes and just like print out the page and cut it and paste it. Probably the easiest way. And then this one, x is greater than 0, y is less than 0. Let's make sure that this makes sense, because that's what you guys are going to struggle with, right? Was making it match, making the differential equation match its slope field. For instance, really quickly, if we were to go in like the third quadrant. So I see the subtraction that gets a little tricky. If we were to go in the third quadrant, there's not very much that we can see, but we do see a negative x and negative y. Well, negative minus a negative, maybe that's not a good one to use. But it depends on the values, right? If this is, for instance, somewhere around -1, if it was going by tick marks, sometimes you have to kind of guess, but if it was a 1 and a 1, -1, -1, what's -1 minus -1? Oh, 0. Okay, maybe that could work.
So it's negative.
-1 minus -1, so -1 plus 1.
But it's -1, so it would be -1.
Ooh, this one's -1, -1. -1,
Oh.
1 would be up there.
Okay.
Does that make sense?
Yeah.
So it does make sense in the third quadrant. We might have some that are 0 when x and y are the same. Wait, when x and y are the same, what line is that when x and y are the same? Y equals x line. Oh, hey, everywhere y equals x, there should be little flat lines because it should always cancel. Ooh, I see little flat lines. Maybe, right? If we were to try something like the second quadrant, where I have x as a negative and y as a positive. If I have a negative minus a positive, question, what are all of those slopes having to be? Negative. Oh, hey, they're all negative. Interesting. How about in the fourth quadrant? X is positive and y is negative. Well, a positive minus a negative, that's going to be a positive, right? All of those, oh yeah, they're all looking positive. First quadrant, oh, they're going to be battling against each other. Sometimes they're going to be the same. Sometimes x is going to be bigger, so making it positive. Sometimes y is going to be bigger, so making it negative. Anyway, those are different ways of trying to think through, right? Guessing certain points, looking at the quadrants, figuring out where the flat slopes are, and measures up. But when they give us a point -1, 1, let's assume that these are by tick marks of 1. How would I follow the flow? -1, -1, -1, +1, maybe there-ish, kind of guessing. But then follow the flow. You don't have to connect anything. This isn't like a dot to dot. You're just kind of following the flow. Now, we do have to have some sort of 0, remember? Because all the zeros are along this line, so wherever this one's going to hit, I need to have some sort of maximum or minimum. Then somehow it's going to go ahead and start coming up. But if I was to have the point instead, 0, 1. Pretty similar. I'm going to have a minimum over here now on that same line. And then it's going to go up again. Right? What if I was to have the point 1, 1?
Family of functions.
Yeah.
So that kind of describes the whole kind of parallel parabolas.
And here's an interesting one. What if I did another one like, let's say, 4, 0. I'm doing one extra one myself. What would that one look like? Well, I go 1-ish, 2-ish, 3-ish, 4-ish. Huh. Does it look like he's decreasing? Well, he's increasing, but to the left he's decreasing?
It probably just goes off the, maybe it just goes off the thing, because those are still a parabola.
Yeah, the question is he going to have me flat? No, because he's not up here. Is he going to randomly go that direction? Not necessarily. So just because it's a family of antiderivatives, depending on what the solution looks like, it doesn't necessarily mean that they're all exactly the same. Some might behave differently depending on their initial condition or the given point. But you still follow the flow. Gerardo, go ahead.
On that last one, because I think that it still looks like a parabola. Because look on the left
Yeah,
side.
but is it the same type of parabola?
No, I mean, if I may, can I?
Oh, well, you're just going to assume that it goes down, and we can't make that assumption based on the graph that we see.
Oh.
See what I mean? So we can't make, I mean, who knows what it could be doing as we expand, but we just have to work with what we have. Right? But this one is oriented up, concave up, and this one is concave down. So I'm just saying that they could be unique in the sense of a different antiderivative might have a different flow or a different shape. Okay. Now what if I was to give you this equation and say, hey, I want you to show me the particular solution. What does this kind of look like? Yeah, it's kind of like a homework problem, and kind of like the example that we did just a second ago. How However, the dilemma is, how are we gonna find a slope field? Plug in points. And maybe, since I see the point 1, 1, that's in the first quadrant, right? Maybe we can just zero in on the first quadrant. And let's not go too crazy, because Gerardo, as you can tell, there can be a lot of points in these, right? So the AP doesn't make you do like 100 points and figure out all the different slopes. That would be ridiculous. But it might give you a few. Might give you 1, 1, 2, 2, 3, 3. We'll just stop there for a minute. And that gives us enough. What are we gonna do? Yeah, we're gonna make a little table. We're gonna have x's, we're gonna have y's, and then we're gonna have our slope, which is gonna be our y prime. We're gonna plug in points, we're gonna get slopes, we're gonna make little baby tangents. Now, we almost got to the end of slope fields. We didn't get totally to the end. I did split the notes up into 3-2A and 3-2B, but it's all one homework assignment. Sorry, 7.1. 7.1A, 7.1B, but it's going to be one homework. So homework's not due tomorrow. We're going to work a little bit more on this, but for those of you guys that are like, slope fields, I got this. You can start on it, but we're going to do a few more, including the multiple choice you guys saw earlier. And then we're going to move on to Euler's method, which is topic number 2 of section 7.1. Sound good? All right, cool kids. Happy Wednesday. See you guys later.